Great. So the pilot site in Weiz, this is the schematic of the system. I added here some notations for the variables I used. So on the left is this tank stratified in 6 layers from temperature 1 at the top until temperature 6 at the bottom. Because there are 6 temperature sensors installed, uniformly distributed vertically, so each layer has same height. Here we have 2, I think, wood chip boilers with different nominal powers, which both feed this hot water to the tank. So this line coming to the tank spreads out. So there is a part of this heat coming to layer 2 and a part coming to the layer 1. And from the demand side, so the demand side takes the water from the very top, from layer 1, and returns it to the bottom. But again, this return is spread out to 3 of the layers, each with a different ratio. So these P numbers are just the parts of the flow. So I'll go a bit more in detail for each of the parts. How is it modeled and which effects we took into account. So first, the storage tank. As I said, it's a stratifying storage layer, and it has input flows at different heights, so it's spread out differently. Also, we modeled flows between each of the neighboring layers. So because this flow comes in the layer 2, it pushes water to layers 1 and 3. But here, the water is taken from layer 1. So depending on the differences between these two flows, the flow throughout the tank will have different direction. It could either go up or down. And this change in the direction changes also the dynamics of the model. So this also gave us some trouble during development of this module. We took into account the conductive heat transfer between layers and the convective heat transfer to the outside air. So this storage tank in Weiz is placed in the partially outside. We took as input to the module the outside temperature, which is measured. So we have the whole profiles of this temperature. And also we took into account so-called buoyancy effect. So when the, let's say, example layers 1 and 2, if the water is warmer or hotter in the layer 1 than layer 2, there will be some heat coming from layer 1 to layer 2. This is the conductive heat. But if layer 2 is hotter than layer 1, the heat from layer 2 to layer 1 will go much quicker. This is called buoyancy because it will actually start to flow, to going up. So then we have heat sources as the second part of the system. So here there is a mixing valve. So when this valve is fully open, so the straight line is fully open and this line is fully closed, it will take water from the bottom of the storage, heat it up, and return it to the upper part of the storage tank. And the whole flow going through the boiler will also go through the tank. But these boilers have minimal required inlet temperature. It is 65 degrees. So if the temperature of the bottom layer of the tank is below 65 degrees, this valve will slightly close this side and open this side. So part of the flow with hot water coming out of the boiler will go in the inlet flow. So it will heat up this water to this 65 degrees. So it also another nonlinearity in our system, which we model to be as accurate as possible. We modeled these pumps of the boilers to have a variable flow. So they're not just on or off. They can change the flow according to the required temperature difference. So in the datasheet, we found that these boilers have a maximal temperature difference from the input to the output, and it is 15 degrees Celsius. So if you want to be to keep up with the datasheet, so to ensure the long life of the boiler, we need to respect this maximal temperature. So we run this pump, so it ensures maximal 15, so 15 or less temperatures in difference. Okay, so besides also temperatures in the boiler, we model temperatures in the, besides temperatures in the tank, we also model temperatures in the boiler, and two temperatures for each of the boilers. First one is the temperatures of the heating block. So it would be like a temperature of the steel inside of the actual boiler that is being heated by the biomass. And the other one is the outlet temperature. So this temperature of the water coming out. The main reason we did this because this boiler cannot heat up immediately. Even though we say, okay, it will go from 0 kilowatt of power to, let's say, 200 kilowatt power, the temperature here will not go immediately. So that's why we have two temperatures that will model this rate change, and also for cooling down. We also model the cooling down of the outside air. So these boilers are not placed outside. So we have another environment temperature that is cooling down the boilers from the outside. I took this temperature to be 20 degrees, but that's just a rough estimation because I suppose it's a boiler room, so it doesn't change much during the day. We modeled this pump to run to extract all the residual heat from the boiler. So when the boiler shuts down, this steel inside it is still very hot, and by pumping water through the heat exchanger, all the residual heat can be extracted. From the data we got from Weiz, we saw when the boiler is shut down, it takes around 2 days to cool down. So I think it was 2 days from 80 degrees to 40 degrees or so. So if the pump runs after the shutdown of the boiler, we could extract more heat and there will be less waste to the air around it. So something more about heat sources, as Mari said, they have minimal and maximal power, or they can be shut off, so the power is 0. Of course, they have variable efficiency, which is quite unusual, I would say. So it has a lower efficiency for the maximal power and higher efficiency for the minimal power. For the price, we took into account wood chip consumption and also the electrical power consumption. This electric power consumption is very low compared to wood chip consumption, of course, but we want to penalize some effects. One of the effects is the base consumption. So while the boiler is on, it has some base electricity consumption, and this electricity consumption goes up depending on power, but there is still this base load. and also it consumes more electricity while starting. So in the optimization, it would minimize the numbers of startups and shutdowns just because of this price. And also electricity is much more expensive than wood chips. And there is also one phenomenon about these boilers, and this is the continuous output of power. So there are two boilers. One is rated at 300 kilowatts and other 540 kilowatts, but they are not suited for a continuous output of this power. So the smaller one is suited for 80 to 270, and the large one from 144 to 480. So that's why we have there, what Mari said, 750 kilowatts maximal, because we never want to go in this area of the maximal power. This is only meant for a short burst of power when needed, but for a long lifetime of the boiler, we should stick with these smaller powers. Then third part of the system and the last one is the demand. So we modeled we have data with this supply temperature and what it should be during the day in the 24 hours. So we put a constraint that temperature in the first layer of the tank must be greater or equal to this supply temperature. Also, we have here this mixing valve that ensures that this supply temperature is exactly as it should be. So the more the hotter the first layer is, this valve will open more for this return loop and less for the direct flow from the tank. And also, as before, demanded power and also demanded flow are predicted. And sorry, didn't mean that. And the return temperature, which is also used in the model, is just calculated through this supply temperature, power and flow demanded. Now that with the model, something about the control, we optimize the schedule of heat sources and their powers. If we have two boilers and we predict 24 hours ahead with 15-minute sampling time, we would actually have 96 values for two boilers. In total, we would have 192 values of powers for each of the 15-minute time instance. So the control is based on this supply temperature, which from the graph we'll see is usually it doesn't change much. So it could be just one single number. Power and flow demand that needs to be predicted 24-hour with 15-minute sampling time. And we also need outside air, but there should be two values, one for outside air outside the tank and also outside air around the boilers. And also this optimal schedule doesn't need to be for each of the time instance. For example, we can group together and let's say maybe we can change power of the heat sources 8 times per day, so we would predict only 16 values. This would ensure not so frequent switching between powers and switch off and ons. Also, we ensure here the state of charge of the tank is the same at the beginning of this 24-hour period as in the end. So we do it as keeping the temperatures same at the 0 hours today, the day we want to analyze and predict, and 0 hours the next day. This means we don't use energy already stored. So if we would have tank fully charged, so the temperatures to the maximum, and at the end of the day we have temperatures, let's say at the bottom level. So this would mean we would use energy from the day before. So it would, the prices we would get wouldn't be so relevant. So we keep sure that we don't steal energy from other days. And for control optimality criterion is the total price in euros. So besides this, the price of wood chips, as I said, there is also electrical power consumption, which penalizes also startups of the boilers. So to show you some example, the upper graph shows the predicted demand of power and flow. The blue line is power in kilowatts, and the red line is mass flow in kilograms per second. And from this picture, you can see that this flow pretty much follows the power, or the other way around. And we can see why also in the bottom picture, where there are temperatures. So the yellow line is the supply temperature needed, which is kept mostly constant at 85 degrees. And the return temperature is this purple line, which is also, again, kept more or less constant at 60 degrees. So I would conclude that the system works in a way that it has set the fixed supply temperature and return temperature, and it changes the flow of the pumps accordingly to keep it that way. So that's why I think we could have just one value for the supply temperature for the 24 hours, which can be easily be entered by the user. And from there, and also would need the power profile. If you have just this one temperature and the power profile, we can calculate others. As we see, the flow will follow the power as the temperature difference of these two is the same. So the green line is this temperature difference. Red line is the environment temperature around boilers. As I said, I put it at 20 degrees, but it's the temperature of the air in the boiler room, which is probably constant, maybe even all year round. And the blue line is the environment temperature of the storage tank, which is placed outside. So this is actually outside temperature, which is pretty low. This is 3 degrees, as it was 1st of January in 2019. So this is like initial simulation, as we thought the automation system would do. So this first graph is the powers used. Blue line, again, is the demanded power from the system. Red line is the power given by the first boiler, the smaller one, and the yellow line is the power given by the second boiler, the bigger one. So mostly the second one is running, but sometimes the first one steps in with some power. And it works in a way that keeps the supply temperature, or the blue line here, which is the temperature in the layer 1. Other lines are temperatures in other layers, going from 1 at the bottom till 6, sorry, 1 at the top until 6 at the bottom. So since the 85 degrees is the minimal temperature needed, it keeps it this way. Sometimes it goes a bit under because there is delay in the system, but it's roughly at this 85 degrees. At the bottom, there are temperatures of other temperatures. Blue line is the temperature of water coming into the boilers, which is this, in this case, same as this temperature T6 at the bottom of the tank. And we have as model the temperatures of the steel inside the boilers. So purple one from the tank, boiler 1, and the green one from the boiler 2. It's not happening much here, but as you see, this boiler number 2 was shut down at the beginning, and it starts here at maybe 4 a.m. So its temperature at the beginning was 20 degrees Celsius as its environment, because it was shut down for some time. And it starts, and inside roughly 15 minutes, it gets to the required temperature it runs. And after the simulation, you would get something like this. So I put in this profile to have 8 different values. So the power doesn't change much during the day. So we're grouped. So the boiler 1 is completely shut down, as this power demand can be fulfilled with just the second boiler. And as you see, it doesn't change much during the day. For the half of the day, it remains constant, which reflects to the temperatures that go up and down. But this is what gives us the flexibility to run the boilers so constant. And as you see, the temperature requirements are satisfied. So the requirement is 85 degrees. As you see, in every step, the temperature is more, even much more than needed. So everything is satisfied, and we used less energy. The price in euros saved, I didn't put here because it's just a bit less, but efficiency of the boilers and the respected constraints are respected. So this is just a closer look at the powers used. The second one, the optimized one, looks much better. So we also we said that we need data measured at the sites to evaluate and tune our model, so we can see if the model we're using is correct. So we can enter powers used at those times and compare our temperatures given by the mathematical model and measured temperatures. And so we can tune our parameters. As for now, we just approximated some of the parameters, especially the heat transfer coefficients, which can have which can be at different values. There's a large scale of these values they can be. So with measurements, we can be more exact. The prices used here are for electricity and wood chips. As seen, wood chips are much cheaper. I don't know if I took the correct prices. For electricity is the same as in Autarky tool, but for wood chips, I'm not sure. If you could tell me, it would be great. And for the end, I have another example. This is from 5th of May. So with less power was needed. There was around 300. This is 200 or less kilowatts of power. So this is initial simulation, simulation of what would automation system do. There's some drop from this required 85 degrees, but it gets the cap, while the optimization tool constantly keeps this 85 degrees respected. And also you can see quite often change in power, and turning off and on both heat sources, while optimization gives a result as more or less constant power just for one boiler, while the other is shut down. And this is just a closer look. And also closer look of the temperatures. So if you have questions, comments, please ask.
One question from my side, Philip.
Yes.
Do you also consider the losses of the storage for the optimization, or only the efficiency of the boiler?
Also the losses of the storage. It's maybe I didn't put it. Yes, I didn't. Yes, convective heat transfer to the outside air. So we have a coefficient of this heat transfer. So from water to steel to insulation to air, and dependent also on the area of the storage tank. So we have all the dimensions, so we calculated the area for each layer, how much it loses energy. Yeah.
Okay, and that's also part of the optimization. So you're not just calculate it afterwards; you use it for the optimization.
Yes, because okay. So it cools down the top layer. I mean, the top layer is the most important one since it provides heat to the consumers, and it's also the most exposed one. It's at the top, and it has more surface area than other layers.
Okay, thank you. I was just asking because I saw in your example after the optimization, the mean temperature in the storage was higher than before. So I think it should not make up too much, but if you have the whole year, it's probably have some influence. Yeah.
Yeah, as from the simulated part, so this outside air doesn't have much influence on these temperatures, but it still should be modeled. As say, this heat transfer coefficient that we use might not be accurate. I see that there's a vast range of values that can be used. So if you have measurements, we can adjust it accordingly. So, but yeah, it is modeled in here.
Okay, thank you.
I wanted just to say that the effect of leakage of heat to outside air is not that dominant compared to the gains you get with changed operation of the boiler. So the optimization chooses to do that and rather to raise the temperature a bit at certain moments. Yeah.
Yes, of course. Just wanted to know if you have considered it or if it's. Yeah. But yes, I'm completely with you. It will not make a too big influence.
Yeah, but it's outweighed. So if the losses would be higher towards the outside air, then you would choose a different strategy. So it's on the level of the optimization, and it would change the behavior of the system in that case. Yeah.
Perfect.